Okay, so here's part two of multiple objects. This is a weird scenario that you're going to do a problem with eventually. But this is like a box hanging from the ceiling from a rope, and then hanging from the box is another box with a rope. And so, quick things you need to understand because there's two ropes, there have to be two different forces of tension. So, again, I'm going to go through individual objects first, and then we can talk about the system approach there. So, for little m, there's like kind of a lot going on. And so for little m has a weight, and so I can put in little mg. But there are two ropes attached to little m, and I can like number the ropes if I want. Maybe I'll call this 1, and this is going to be 2. Then I can have Ft1 is a tension force above little m, and then down here Ft2 for the downward force. So there's two downward forces because we have the force of gravity, and then there's a rope that is hanging from mass m, and so there have to be two tensions there. So if I think about like the net force on mass m, it's going to be Ft1 minus Ft2 minus mg. And because these boxes are not supposed to be moving, that's equal to 0. So that's little m. And then for big M, it's simpler because there's just the force of gravity, and that's capital Mg, and there's only one rope. Now, because it's the same rope that was attached to little m, I have to use the same tension designation. And so I use that tension was Ft2. And so there's two forces there, and that's for the hanging box at the bottom. So the net force on this one is going to be Ft2 minus big mg. And then that should be equal to 0 because nothing's accelerating. And so I'm going to just kind of cut this example off now and say, well, we have two equations and they have a tension in common. The last thing I wanted to do was do the system approach. And so if you would like to call this M and M, you may. So big M and little m are the same object now. And if I draw a free body diagram for that big object, what happens is this second rope down here is now inside the system. So it can't appear on the free body diagram because it's an internal force. So gravity is the obvious choice for internal force. And this is kind of complicated because it's both of their masses times little g. So they have a combined mass, and so they have a combined force of gravity. And then the upward force needs to be Ft1. And so the system approach, again, kind of like makes things simpler for you because there's fewer forces. You really just have to make sure you're on top of things as far as the mass. And so the net force on this one is going to be Ft1 minus combined mass times g. And again, that's equal to 0. And so, just take a look at this. There are obviously connections between the expression in red and purple, and then the expression in gray. Because they are the same system, they should produce the same results. And so I'll leave you with those equations because the question could be different depending on what you're analyzing. The last example I wanted to do for multiple objects is called an Atwood machine. And this one I'll go through maybe even more quickly because I want you to kind of puzzle over this. But the idea is this huge thing in the middle is a pulley. And there's one single rope draped over the pulley, and there's a mass at either end. And the masses are not the same. So, we can always take like big M is going to be the greater mass than little m. And so when you let go, the heavier one starts to move downward and the lighter one starts to move upward. And so this is basically it's a machine that's sole purpose is to demonstrate physics concepts, or Newton's second law, or some rotation concepts. And so I would again encourage you to think like, okay, well the pulley is going to rotate this way because that's the heavier mass. This is now the positive x direction. So little m accelerates in the positive x direction, which is up, and big M accelerates in the positive x direction, which is down. When you draw a free body diagram for these objects, you want to do it in context, meaning big M has gravity and tension, little m has gravity and tension. Those are up and down. But when you start to combine things, recognize that they're going to have the same acceleration, and it's going to be in the positive x direction. So what might be a positive force for big M is going to be a negative force for little m. And so that one is just kind of like a teaser where you kind of get some advice, and that's it. So I'll ask you to work with this in one of your problem sets. And then, if you take the system approach, that eliminates the rope. Because the rope is internal to the system, it's really just any leftover external forces that are going to cause acceleration. So again, I'll leave you to kind of work with that, but hopefully you have enough to get started. And that's it.